manajemen energi. Teknik fisika.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. My name is Metha Islameka. So today I'll present about energy consumption simulation and analysis of rain-driven electric bus with regenerative braking. So here's the contents. I'll divide the contents the four subtopics. There's the introductions and the experimental methods, which will also explain about the electric bus specifications and how we model the electric bus energy consumptions, and also we'll explain about the collected driving cycles. And next is the results and discussions. We'll present about the electric bus model and how the comparison results. So I'll be compare two electric medium bus for some driving cycles that are collected, and last one is the conclusion. So for the introduction, it's already know that Indonesia's government Indonesian government is planned to change the bus transportation, especially in Jakarta, to be an electric bus. The reason is we could say that 70% of air pollution in Jakarta is caused by the combustion engine vehicles, and buses and trucks contributed gas emissions in the form of carbon dioxide by 47.72% and 33.26% respectively. So electric buses could be the main solution to reduce air pollution in Jakarta, as we already know. It has some advantage like zero emissions, reduce noise pollution. Next, the plan is using the electric bus will be used for Trans-Jakarta Corridor 1. And here we simulated two types of electric bus medium. This one is from ITB electric bus, and it's the BYD-C6, to compare their energy consumptions in Trans-Jakarta Corridor 1. So in this work, analysis of the energy consumptions of the real-drive electric bus is performed to show which electric bus specifications are better for the certain driving cycles, which is the route of the Corridor 1 Jakarta. So here's the experimental method. Here's the specifications of the bus from the RGB and the BYD-C6. The specifications actually not really different, but because some data from the BYD-C6 not provided, so there is some assumption data that I'm using, like the wheel radius and the total gear ratio. And for the electric motor, here's the specifications. And it's the battery specification. Here's the modeling, how we model the electric bus energy consumptions. So for the input, I'll using the driving cycles of the what I said before about the Trans-Jakarta Corridor 1 Trans-Jakarta. It's so one cycle of driving is like the back and forth from Kota to Blok M and to Kota again. So we could actually the conditions 3 and 4. Here's the condition 3 and this is condition 4. Needs more time. So So which means it is there is the heavy traffic in that condition. So I collected four conditions for driving cycles. But I'm not using the raw speed data that I collected. So it's because we'll see at the first 100 seconds. So I'm doing some filtering data for the driving cycles data. The first one that I'm doing is compare the data from the applications, from the GPS, from the recorded speed data, and from the calculated. The calculated means like we already know how the GPS works is they give the signal to the satellites and gives the position signal back to the GPS. So I'm trying to compare those two from the recorded applications from the GPS and the calculated one. But because that's how we already know about how the GPS works, so I'll be using the calculated one. And the step 2, data filter step 2. Actually, when we're using the GPS, there is we also get the longitude and the latitude about the positions. So when I check all the longitude and the latitude, there is some point that should be like this. There's on the 70 seconds till the 100, it should be in the 0 meter per second. It's because if I see at the longitude and the latitude, it's supposed to be at the shelter. So I'm change it. And the data filter step 3 is to fill some blank data using the linear interpolation. Next, for the last one, because we can see that there is some data spike, I'll be filtering it by compare to the so there's a regulations about the brake strength, which are limited to the 0.8 g or gravity acceleration. So I'm trying to changing some of the data who's more from that limit of the regulations, that 0.8 g. And here is the results of some of the changes. Like you can see, here should be the shelter, so it changed to 0. And here's the model. So there are 5 components in the model. The first one is the driveline. It based on the Allenberg principle, that says a dynamic system can be simplified into a static system by adding a fictitious force, or also known as an energy. This is the equations. So the driving force, it will be the sum of the resistance. And here's the equations for the resistance. And for the braking system, the traction force that we've got from the driveline component will be divided to the front axle and the rear axle. And here's the definition. And for the gearbox components, this will be just change the dynamic of transmission to the rotation, and the electric motor will be calculate the power where the torque of the motor is limited to the maximum the specifications of the motor. And the last one is the battery. So from the power that we've got from the electric motor component, we'll calculate the current, and from that calculated we could get the power of the battery, and from the power of the battery we could get the energy with these equations. So the output would be the SOC. And here's the model. So that it's the input, the output, and here's the model like what I put in before: the driveline, the braking systems, the gearbox, the electric motors, and the battery. So for the driveline, is based off the vertebral circle and divided the positive force and the negative force. And the negative force will be the input of the braking system, and we're going to divide it to the front axle and rear axle. And we're going to the motor. Yes, we limited with the maximum specifications of the motor. And then for the battery, we sum up all of the power. Like it's just the same with and here's the comparison results. So we could see that the ITB electric bus needs more energy. Like we already know, if we look up at the specifications, the ITB electric bus has more or greater weight, and for the comparison between the non-regenerative braking and with regenerative braking, the ITB electric bus can recover more energy due to the better, more specification. And because we've already seen the conditions 3 and 4 it's heavy traffic, so it's just that yeah. So it's the conclusions based on the simulation that has been conducted, separately done to get the optimal electric bus designs. And in the future works, because I'm still doing the filtering data manually, try to make it automatically and compare directly to the data measurements, because it's using some constant data for the specifications.